All right, everyone. Welcome back to System Software. So today we're going to continue with the front end of the compiler, looking at how the input language gets processed. Just a reminder that the Toy Compiler 2 is due this evening. And I've put up the homework for today, for next week. And also keep in mind that the Simple C compiler, that's going to be, you got a couple more weeks to do that. Hopefully it's not too bad, but get started early. Let me know if you have any issues. Come to office hours. Questions on the homework, questions on Toy Compiler 2, on the Simple C project? Yeah. OPT? Where are you seeing this? Oh, it means optional. So as in like this construct may be there or may not be there. It's like function arguments. You can have functions without any parameters, and so it's just short for optional. Questions on anything we went over last time on semantic actions, abstract syntax trees? This hopefully is everything you need in order to do the Simple C for a Simple C project. Also a note, per request, I added a little bit more information about the AST API that I've given you and how it maps to the grammar. So I've given you a list of all of the non-terminals in the language and which AST type they'll have, so that should give you a hint as to which AST constructor to use, as well as for the terminals, what types they are, so that'll help you figure out what the parameters to the functions are. And I've also given you the list of the AST creation API mapped to the construct, the name of the construct in the grammar. And one part that's a little more subtle is the operators. So these are represented with an enum. And these are the actual enum values for each operator. You'll see this when you actually go to translate or create an AST, construct the AST for the expressions. You'll see, well, what do you put for the operator? So for instance, this unary expression, like minus x, or dereference x, that's a unary expression. And in the grammar, it's called a unary expression. And this is the AST function to create the AST node for the unary expression. But you see the types are this enum type and another expression node. So the expression node comes from the child of the unary expression, and the operator comes from the operator. So you'll see in the grammar that there's grammar constructs for each operator. And then, in the semantic action, you'll return that corresponding operator enum. And similarly for the primitive type names. So hopefully this will make more sense when you actually work on the project. And you can use this table as a reference to help you figure out which data types that I'm expecting you to do. So I designed this. This is I've given you a template, and so part of the challenge is understanding the template I've given you, but hopefully it'll be easier than doing it from scratch by following this. Questions? Okay, so good luck on the front end assignment. So for the rest of the next couple of lectures, I'm going to be explaining to you how these parser generation technologies work. So you won't have to implement the parser because they're generated for you. And this is really classic computing. You'll probably see this in discrete if you've taken it or you're going to take it. This is like classic pattern matching techniques, and they're so sort of well known and well understood that few people even bother writing these anymore. Instead, they use Flex and Bison and other libraries that will actually generate code for you to do this. So they're kind of like mini compilers. You give it some specification in this language. For for doing pattern matching, and then it'll generate code for you. That's what that parser.y was in your toy compiler. It was generating parser.tab.c. It was generating code for you. All right, questions before we begin? Okay, let's get into it then. Regular expressions and finite state automata. So let me motivate a little bit what regular expressions were designed for. So for instance, let's say you wanted to just match phone numbers. Maybe you're a scraper and you're trying to populate your robocaller with a bunch of people to nag for marketing, and you want to scrape phone numbers or email addresses off the internet. There's a lot of ways to do this, but how would you say write a program that would search for the pattern of an email address in a text file? So how might you do it? Yeah.
I would look for the at symbol and then go backwards until I would find a space if I'm
Okay. So the answer was, well, I would look for the at symbol and then move backwards and look for the name, move forwards, look for the domain. So how might you? So what would that look like in code? How much you? Okay, we're back. So how would you? How would you search for? How would you look for the at symbol? Okay, so you'd like get each character, read each character in. Read each character. Maybe I don't remember what it is. Let's call it, say, get char. You'd read it in, and then what?
And then check if it's mad, if it's not.
So if it equals, okay, and how would you keep going? While loop. You'd have some iteration, and you just kind of repeatedly look each character, one character at a time, until you get some kind of match. Yeah, I mean, all these string algorithms, probably learned in CS1, CS2. You're basically just reading in characters one at a time. You're using the tools that are given to you in the C language, like iteration. You're using conditionals to say, okay, if I've matched this character, then do some other action. And so you could sit down and you could probably write this program. I'm sure all of you could do this. But what regular expressions do is they abstract away this problem into a new language called regular expressions. And so pretty much every programming language has a library for you to do regular expression processing. Who's used regular expressions before, like in practice? Okay, not too many. But they're pretty commonly used for doing just string pattern matching. All right, so let me give you a little example in Python. So there's this nice demo program in Python, which is here. Who cannot read this? If I type characters here, cannot read it. All right, give me. Okay, apologies for that. Okay, so with regular expressions, we can write a little pattern matching, a little pattern that the regular expression engine will match for us. So at the simplest, we can just match a sequence of characters. So if I want to match cat, this is my pattern that I'd like to match. And in the box here, I can write some sentence like, I have a cat. You can see here that the regular expression engine is matching CAT. So not super impressive, right? You could easily write a program that just loops one at a time from each character and checks, okay, is that a C? Is that an A? Is that a T? What if I'm trying to match the original problem I was talking about, where we're matching, say, a phone number? So let's put a fake phone number. So how might I match any arbitrary phone number? What would I have to do if I was just not matching an email address where I look for an @ symbol? How would I match, say, only numbers? How would I do that in code? So we had our code example where we used a while loop to iterate over the program. Yeah. So that's the regular expression language. How would you write? But how would you actually implement that in code if you didn't have a regular expression? Right. Yeah, you would look at the ASCII values. But how would I write? So if I just want to match one digit, how would I write that in C code? How would you write a C program to do that? Yeah. Okay. Yeah, you could check the ASCII code. What if I want to match just 0 or A? Yeah. You'd say is it? Yeah. You'd say, well, you would do a conditional, right? You check with a conditional. You read each character, and you check. Is it 0? Okay, I'm good. Is it not 0? Okay, I'm not good. And if you had a sequence of these characters to check, like let's say I wanted to check. So yeah, as a trick, you could exploit the fact that ASCII it's continuous. But if I wanted to check if 0 or 3 were there, then I'd have to iterate through each character, write a conditional statement, and say, is the character C? Is the character A? Or is it C? Etc. And if it is, then I have a match. Otherwise, I need to move on and continue checking characters. And so those who are familiar with regular expressions probably know how you can do this. So one is character classes, which someone mentioned. But the other way to do this is with alternation. So with cat, I just wrote one character after another, and that pattern said I want to see this sequence of characters in my input. With alternation, I can use this pipe symbol to say or effectively. Sort of like logical or, but it's not actually logical or. And I can encode every character that I'd like to see. So let's say I wanted to see 0 through 9 in my input. Then anytime I see a digit in my input, I get a match, highlighted by yellow. Otherwise, I don't get a match. Questions about this? Does this kind of make sense? So there's a little language we can define here to say, give me this character, or this character, or this character, and so on. But notice here, only a single character is being matched by this regular expression, notwithstanding this highlight all matches argument here. So just like with math expressions where I can do an AND operation, then do multiplication, I can use parentheses to define orders of operations, I can combine these regular expression operations in the same way. So I can say, okay, let me see either one of these characters, and then afterwards, I would like to see cat right after that. So if I've got a random sequence of tokens, and I want to highlight whenever I see one of the digits in here, followed by CAT. Yeah. So space so how is space represented in ASCII? I think we talked about this a couple weeks ago. How is space represented in ASCII? What's that? Null? Is it null? Who says null? Who says something else? Yeah. Oh, what do you say? It's another ASCII character. So just like C or A or T, it's another ASCII character. It's a non-printable character. The terminal doesn't have to do anything for it besides update the position of the characters. But yeah, I could put a space character. But remember, a space character is just another ASCII code. And I think I can show the ASCII table here. So there's space right there. So it's just another ASCII symbol, just like exclamation point or 0 or A. And so it's a little hard to see looking here, but I can add a space between the number and C and A and T. And notice that my highlighting here, I don't get a match for this anymore because I've required that we have some digit followed by a space followed by CAT. And so if I see this pattern in my input, some digit followed by space followed by CAT, then my regular expression will match it. Questions on this so far? Yeah. And make it do what? That's a good question. So do we have any, so we've seen concatenation where you have one character after another, and we've seen alternation where you can specify a choice between characters. So is there some operation from what we've seen that we can do to say, I'd like to see a character or not see a character? Yeah?
You could do, like, say, in parentheses, space C or C.
Okay, so you could say, so what your fellow student is saying is I could say I either see a space or, so it's a little hard to read. Let me just do this here. So I either see a space or I see the character C. So in my input, I can put C and it'll match. Or I can put a space and it'll match. Yeah?
I was saying it's space C type C. That'll give you a space followed by a C or a C. What is that?
Oh, sorry. So you were saying space C. So let me make this a dash so it's a little easier to see, or maybe an underscore so it's a little easier to see. So space is very hard to see, so I'll put an underscore here. So this is saying underscore C or C. And so in my input, if I say I have 3 underscore cat, then it'll highlight the underscore followed by the C. But I can also say I have 3 cat, no underscore, and C will get matched because there's 2 options here. Either we match underscore C or we match C. And parentheses, just like in math operations, are just order of operations. They only tell you which operation to do first. They don't have any computational meaning, just like in and in or. Yeah?
Mostly when we were typing the numbers, how did you get it to recognize the space between the numbers?
So we just literally put the space in our pattern. So we put the space character in our pattern, but it's just hard to see space in our pattern. Yeah. Kind of like what? It is in a sense distributive. It is. It will be. Yeah, in a sense it is. You can think of OR like plus and concatenation like multiplication. So you could actually rewrite it to distribute it that way. Yeah. So yeah, let me take one of these examples that look like in the homework, one of these more abstract ones, to illustrate this. So if I've got A or B, parentheses, so I either see A or B, and then followed by A, B, B, what are some examples of characters, or what are some examples of strings that will match this regular expression? Yeah. Okay, double A or double B, or what was the other one? B, A, B, B. So you can see, so I've just turned this option to check for the whole string for matches. And so what are some examples of strings that don't match? Yeah. String of C's or that I wrote here. Okay, good. Yeah.
A.
Say again? A, B, B. So yeah, A, B, B didn't match, though B, A, B, B matched. Yeah, it's exclusive or. So either A or B, but not both. So it's not really a logical or, it's alternation. It's I either see this character or I see this character. Okay, so I know these are really simple patterns. You can only, check alternative characters and sequences of characters. What makes this more powerful is that you can do repetition. So I can specify, and here we can only specify finite strings, a finite set of strings here. So you can actually use distribution, like your classmate pointed out, to compute all possible combinations of strings from OR. You just expand out, distribute the OR, distribute concatenation across every possible OR. But we can also match infinite sequences, an infinite set of possible strings, with this special operator called clean closure. Clean closure is represented by a star. If you've ever seen this in regular expressions, it's always a star. Like wildcard, when you type ls, star.txt. It's a similar idea, although that's more like any character star. So what does star do? Star matches 0 or more sequences of that character. So for A, this matches A. It also matches 4 A's or 5 A's. And so you can see anywhere in my sequence, it matches any set of possible A's. Why is it not matching? Oh, I see. It'll match any sequence of A's in my input. And so, for instance, I can use this to, say, match cat with any sequence of A's inside instead of just one A. So, for instance, if I have C, A, T, that will match. If I have C, double A, T, that'll match. And any sequences of A's followed by a T match. Cat, yeah.
Will it work with CT?
What's that?
Will it work with CT?
CT? That's a good question. Will it work with CT? So star means 0 or more. So if I've got CT, then that's 0 A's between C and T. So yeah, it works with CT. Yeah. Say again?
They have to all be in one string, right?
Well, so it's one character after another. So when the characters are adjacent to each other, the character must follow immediately afterwards. So it ends up, the operation, you're telling it with the concatenation operation that it must follow in a sequence. Yeah.
So if we put B in the middle of a string of A's, then it's not going to
Put a B, yeah. So if I put B here, does not match because the pattern says I must have C followed by 0 or more A's followed by T. So if I have 0 A's, T must come next. So if I have CBT, then no match. Yeah.
If you wanted to ensure that there was either one A or more, would you put C A star T?
Well, let's see if that works. So if I want to ensure that there's at least one A, then this pattern says I must see a C, then it must be followed by an A, and then it should be followed by 0 or more A's. So if I have some long sequence of A's, that matches. If I have 0 A's, then my pattern doesn't match because it's supposed to see C, and it must be followed by an A, and then 0 more A's. So this string here doesn't match this pattern. Doesn't match this pattern because there must be an A afterwards. But yeah, good point. So if you want to do one or more, you can encode that with A, whatever your expression is, followed by that expression star. Question? Yeah.
I don't know, like, just for writing more, like, the characteristic finite automata and non-deterministic finite automata.
Yeah, we'll get to that. We'll get to that in the next. This is how regular expressions are implemented. We'll get to it. Yeah.
Then we do match pattern n amount of times instead of
N amount of times. Yeah. So how might we say? Let me match 10 n's. How would you, is that what you mean? So how would I match 10 n, or 10 a's? So I want to have cat with 10 a's in between t. How might I write a pattern to match that? Yeah. You just type out 10 a's. Yeah, so you would just type out the 10 a's, and that's your pattern. So with the operations we've seen so far, concatenation, alternation, and clean closure, we can't express that. We can't express C followed by 10 A's followed by T. It's just that's how we do it with those three operations. Now there are extensions to the regular expressions that add things like, and a way to express match 10 A's. You know, I don't remember, I don't know if there are any languages that do 10 specifically, but you could make up a language to say like, to add new symbols to the language, just like we do with the programming language, to mean, give me 10 A's. There are languages that do this. I just can't remember the syntax for this. Or match, say, between 0 and 10 A's, or something like this. So how would I match, say, I want to see 1 or 2 or 3 A's in between cat? How would I write a regular expression with the tools we have now to do that? Or is that possible to write? Yeah.
Simply 1A or 2A.
1A or 2 A's or 3 A's. Yeah, so we'd write it like this. So we'd use alternation. We'd use what we know about how to match a finite sequence of characters, 3 A's, 2 A's, 1 A's, and then use alternation to combine those different patterns together. And now our input should be able to, so I can match a single A matches, 2 A's matches, 3 A's matches. But if I do 4 A's, I don't get a match. Because when I saw the 3 A's, I should have seen a T afterwards, but in my actual input, there's an A after that, those 3 A's. Yeah? There's a library for it, yeah, in Python, regex, for regular expressions. And most languages support doing this kind of pattern matching. Questions so far? Yeah? That's right, yeah. So it's supposed to be 3 A's. Why is it not matching? Around. Oh. I thought concatenation was higher precedence. Oh. Oh yeah, I see. So just to avoid any precedence issues, I thought it was higher precedence, but maybe I'm wrong. I guess I'm wrong. Or I don't know. So T star. That's weird. This seems wrong. Oh, I'm highlighting all matches. Maybe that's why. Huh. Let me just try CAT star. All right, I don't know why that's, why so that still works. Okay, I don't know why it wasn't working before, but it is matching now. Maybe something was wrong with how they update their pattern. But yeah, this is what you were saying, right? Infinite number of T's. So CA or CAA or CAAA followed by 0 to any number of T's. And so with these 3 simple operations, we can match a whole range of different string patterns. And the kind of notable thing here is that we can represent an infinite number of possible matches with a finite expression. So just like in a C program, you can have an infinitely executing program, but the program itself is just a finite piece of code. It's the same idea here, where you have finite representation, but infinite set of possible strings. All right, questions so far on this kind of slightly arbitrary, but hopefully illustrative examples of these three operations for regular expression pattern matching. Okay, so how would we do this phone number matching? So let's say, I did want to say, so how would we match phone numbers using the tools that we have? Yeah.
You do the 0 or the 9 and then do the 3 times dash.
Okay, so we know how to match one digit using alternation, and there's our first digit matching. And then we can just use concatenation to concatenate each of these patterns 3 times. And so we've got our first 3 numbers matched. And so I can match any sequence of 3 digits. So there are extensions to this language that make it easier to write these. This is going to be very verbose if we have to write this. So this program uses Perl-style regular expressions, and so I can match a character with /d, or use, as somebody suggested, character class. But this is all, you can look at your library's language extensions to do this. Yeah.
How would one search for parentheses?
So yeah, this is a language problem, since, or a pipe, right? How would you search for a pipe? Is that what you mean? Because parentheses are used in the expression. So most of these regular expression languages have an escape character, just like \n allows you to write an enter, a new line character, even though new line characters are non-printing, so there's no way to write it. So I can just escape the character in my expression with a \. So if I want to match any digit followed by a parenthesis, then I use the escape character for parenthesis. Okay, so I can use this \d to match any digit. This is like Perl style syntax. And just like your fellow student pointed out, we can concatenate 3 of these together, and this will match any sequence of 3 digits. And then how would I match the hyphen? What's that? Yeah, you just put hyphen. You concatenate any alternative of these 10 characters, or 10 digits, then followed by that same pattern, followed by that same pattern, followed by hyphen. Yeah? That's a good question. So how could you say match everything but 9? So how could we write something that will match these digits except for 9? You just do the OR. So it's verbose for sure, but now you can see that if I do this 3 times and try to match 439 won't be matched anymore because it's not a sequence of 0 through 8, followed by 0 through 8, followed by 0 through 8 anymore. We have 2 characters that are 0 through 8, but the third one is 9. And so this sequence of 3 possible characters doesn't get matched. So there are easier ways to do this in extensions of regular expression languages like character classes. So I could exploit the fact that the ASCII code is lists out the characters sequentially and just use this character class. But don't worry about that too much. You can learn these kind of in practice if you need to use regular expression languages. But yeah, this is how I would match using regular expressions a phone number. I would just have 3 digits followed by hyphen, followed by 3 digits, followed by hyphen, and for like a US number, followed by 4 digits. And voila, I've matched one variation of the of phone numbers, and there's lots of them. So this may or may not be the best choice for doing this, but this is how you can do pattern matching with regular expressions. Questions on this? Okay. Okay, so those were just to highlight, those were our three operations. We've got, sorry. We've got sequence or concatenation, where we have one character after another. We have alternation, where we have one character from a series of options. And we have repetition, this clean closure. So if you want to learn about this and play with this, you can look at, here's some examples to look at that people use in practice. And here's our language. It's just like math expressions. We have a language to define expressions, regular expressions. Concatenation doesn't have an operator. It just puts characters next to each other. We use pipe for alternation and star for clean closure. And there are lots of variations of this. Lots of variations in these regular expression languages. So like the Python library that I used for this example. It'll tell you all of the special built-in character classes that you have. They'll show you the extensions, how to call it and everything. You can match the beginning and end of a line. So anyway, so these are really useful in practice, I think, for like practitioners. Sometimes you may just need to do some string pattern matching. So given one of these expressions, we could, hand write a program using if statements and while loops and reading characters in to actually do this matching. But it'd be much more useful if we could take this expression, just like a grammar, take this expression and generate a program for us that will do the pattern matching. So this gives us a way to express the patterns, but how can we actually write a program that will match the pattern? And so let's not do this by hand. Let's automate this. This is kind of the spirit of compilers. If you can come up with a language for specifying your problem, then you can generate code that will solve the problem for you instead of having to write the code by hand. And so this is where finite automata come in. So who has seen finite automata before? Okay, not that many. Is it in discrete, small discrete? Discrete 1 teaches it, right? Discrete 2. Oh, okay. So we're getting a little preview of discrete 2. So it's not going to be as rigorous as that, but I'll give a little high-level overview of finite automata. We'll see how to use them and how they're used to implement regular expressions. So there's an example of a turnstile, which I guess these still exist to some degree, right? Maybe not that much. But if you think of a turnstile, you have to put in money or a card or some mechanism to unlock the turnstile, and then it turns once, and then locks again, right? You all use turnstiles, I think. Are they still being used? Or is it all like digital now? They still get used. And so we can model the behavior of this turnstile with states and transition between states. So there's only two states of this turnstile, either locked or unlocked. And there are two operations that you can do to change the state of this turnstile. You can either push the turnstile, or you can put a coin in, or whatever your authentication mechanism is. I mean, decades ago, subways had token. You would actually physically put a coin in. I'm old enough to remember, I guess. Now it's all digital. But there are two operations you can do. You can push it, or you can put a coin in. And we can model this system as the states that it could possibly be in, all the possible states that the machine can be in, and all the possible operations that change the states of this machine. And so this is really the first mental model that I'm introducing to you in this class. Remember, I talked about weeks ago in the first class that having some mental model of your computation helps you solve problems better. So if you had to just implement a digital turnstile, you could sit there and hack together something in Python with if statements and while loops. Or you could see if you can map the problem to an existing model of computation. And if you can map it to finite state machines, then you can use regular expressions. So regular expressions can be written to basically model what a turnstile does. You actually implement what a turnstile does. And so here is how we diagram a finite state machine. We use circles for states. This is the kind of convention. This is not so natural law. This is the convention we use in computing and engineering. We use circles to model states, and then arrows to model transitions between the states. And on the arrow is the name of the operation that causes the transition. So some symbol that represents the thing that causes the state transition. And so here's the model of that turnstile behavior. If we're in the locked position and we try to push, well, the machine is still locked, right? We don't want to open it until somebody puts a coin in. When somebody puts a coin in, we enter the unlocked state. And I guess this turnstile just steals people's money, because every time you put a coin in, it stays unlocked, but as soon as one person pushes, it goes back to the locked state. So what if it's unlocked and like 10 people put coins in? Are all those 10 people going to go through? Not in this machine. You need a different model of the machine to be able to handle that. But for a very simple turnstile, we can model it like this. And this actually comes out of the engineering world, electrical engineering world, where they would actually build circuits that are finite state machines for like traffic lights and probably turnstiles and things like this. I think nowadays it's probably microcontrollers. But this came out of the engineering world to kind of have a model for all the possible behavior of your machine. Okay, questions on this? Questions on the diagram? Who's seen these diagrams before? Okay, so more people who know about finite state machines. That's interesting. Okay, so it turns out that this type of machine, this model of machines, this finite state machine, correspond to regular languages. So if you've got a regular expression that has these, any pattern matching expression that has alternation, concatenation, and sequence, any regular expression can be mapped to a finite state machine, and vice versa. There's a correspondence between these two, which kind of surprising, right? That you have this language, this math operation that you described, corresponds exactly to this state machine model of computation. And so what that means is that our regular expression, which is just text, it's just something on paper, a kind of conceptual thing, which has no computational meaning to a machine, if we can map it into a state machine, then we can build a machine that will actually match that regular expression. So kind of just like what we're doing with our compiler. We have this C or simple C language, which has no physical computational meaning. It's all in our heads, it's all conceptual. And the compiler maps this to a set of instructions that actually run on a physical machine. So you can think of this as like the very first kind of compiler, very first kind of fundamental fruit fly of mapping languages and specifications to physical machines that can actually do computing, that can actually do state transitions, do something in the physical world without you thinking about it. The machine will actually act autonomously. These have other names, sometimes finite automaton, finite state machine, but they're all the same thing. And it turns out that this linguist, Noam Chomsky, decades ago, found this hierarchy and this mapping between computation and languages. There were other researchers who looked at this as well, like Clean Closure. But he developed this hierarchy of languages that have increasing degrees of expressive power. So regular expressions, you couldn't say, write certain kinds of programs with regular expressions. You can do more in a C program than just do regular expression matching. And he discovered that there was this hierarchy of languages, and more importantly for us, these map to a computing machine. These map to different models of computation. And so the kind of amazing thing here is that language and computation are these inextricably linked things. They can be mapped between each other, and this is why a compiler can work, because we can map a specification language to what a machine actually does. And so here's the hierarchy, and we're going to look at a couple of these in this class. So we looked at regular languages. These are languages that can be expressed with regular expressions. And these map one-to-one to finite automata. But as we'll see next week, there's all sorts of patterns in languages that we cannot recognize with a regular expression, especially when it gets to infinitely nested things like nested if statements. So that's where context-free languages can match a larger set of possible patterns. And this is where parsers come in. And we'll look at this next week. The formal model of computation for this are called push-down automata. Who's seen push-down automata? Okay, very, very few people. Discrete 2, I think, will do this. But yeah, this is more unusual. But it's effectively a model of what the parser does. And we'll look at that next week. Then there are context-sensitive languages, which correspond to non-deterministic push-down automata. And then finally, at the highest level of expressivity are these recursively enumerable languages, and these correspond to Turing machines. So we're not going to look much at the last two of these. The first two are used in the parser front ends. I mean, technically, the specification of the language is equivalent to a Turing machine in simple C, if we have infinite memory. But we're not going to look at ways to automatically map between the two. There's other techniques to generate code. All right, questions on this? So this is more of like an intellectual curiosity and something that's interesting intellectually, but we're going to use this practically for these first two to actually help us automatically generate the first part of our compiler. So you may not use regular expressions or parsers, if you become an engineer, but what I want to kind of get into your mind is that if you pick the right model of computation for your problem, it can be much, much easier to solve it. So if you know that you don't need a Turing machine, you don't need full computability, you can use a simpler model of computation where researchers have already found ways for you to just specify the problem and generate code for you. Just like if you don't have to write assembly most of the time, you can just use C or a high-level language. And so, think, what's the model of the problem that I'm trying to solve, and can I map it into an already existing mental model? So for finite state machines, there's a whole bunch of applications that can be mapped into regular languages, where you can specify the problem in regular languages. So, simple things we see in the world nowadays, or now we think of them as simple, like vending machines, turnstiles, traffic lights, anything where you can list out the finite set of states, and those are finite, you can model that computation with a finite state machine. It may not be the most convenient way, if you have maybe billions of states, but you can do it. As long as you can identify the finite set of states and then the operations that transitions between those states, you can use basically a regular expression or a finite state machine to do that computation. And there's already tools available for you to do that kind of computation. And importantly for us, lexing, the job of tokenizing the input in our language, identifying words in our language, this can be mapped to a finite state machine and expressed with the regular expressions. So that's when you guys wrote lexer.l in your toy compiler, that's what you were doing. You were writing out all of the words or tokens in the language as a pattern in this regular expression, pattern matching. There are also some more either humorous or interesting ways to use state machines. So for instance, in gaming, at least in classic gaming, state machines were used to model the behavior of, say, AI in the game. So, is it searching? Is it shooting? Is it dying? Is it spawning? These are a finite set of states, and you can make a little machine that will model the behavior of these characters. Somebody also tried to create a regular expression that described all of the valid movements in this Game Boy game, Pokemon Blue. It's kind of a funny YouTube video where he just wanted to be able to check that the sequence of inputs is actually going to lead to a winning game. And you can see how successful or not he was with doing that. But basically anything in computing where you know the set of states, you know the operations between them, you can model using finite state machines and regular expressions and express them with a regular language. Okay, so let me just give some definitions here. So in this notion of formal languages, With formal languages, at least the ones in this Chomsky hierarchy, a language is defined as a potentially infinite set of strings. And each string is drawn from a finite alphabet. So your alphabet's finite, like the sequence of ASCII characters. The number of possible strings in your language can be finite, can be infinite or can be finite. So when we wrote, say, cat with any number of A's in between the C and the T, we were defining an infinite language of all possible strings that start with C, end with T, and have any number of A's in between. But it can also be finite when we just matched cat with 1, 2, or 3 A's in between. But they're also drawn from a finite alphabet. So this is trying to model, like, originally, Chomsky and linguists were trying to model human language, where we have a finite set of sounds and a finite set of words, more or less, but we can express an infinite, potentially unbounded or potentially infinite number of things with that language. So automata, the definition of automata is related. There's a finite set of symbols, just like in regular languages. There's a finite set of states. You have a state transition function, which maps between your input state and your output state. And then you have initial states and final states. And I showed intuitively the diagrammatic representation of this, but there's a few extra features of this graphical representation, some conventions that we can use in order to track the input states and the accepting states. So just like before, states are circles, transitions are labeled arrows. The starting state is an in arrow with no preceding state. And accepting states, when you've successfully matched the input, these are with double circles. So here's an example of matching identifiers in our language. So if our language, like in C, has identifiers that must start with a letter, but then it can be letters or digits, and C underscore as well. But if we have a language where we want all identifiers to start with a letter, and then you're allowed to put letters or digits inside the identifier, this is what the state machine might look like in order to match that input. So other here is just all the other characters in your language that are not letters or digits. So if this is the ASCII symbols, it's all of the characters minus letters and digits. And this is what the state transition diagram for this finite state machine might look like. You start at state 9, so this is our in arrow that has no preceding state. And if we see a letter in the input, then we move to state 10. If we don't see a letter in the input, what happens? What's that? If we don't see, so what's sort of unspoken in these diagrams is what happens when you don't see, at least when diagrams are written, state transitions for letters other than the one that are on one of the state edges out, they're not shown. But yeah, do you have an idea of what we could do with those? Yeah, you're going to say something? Yeah.
Do nothing.
You could do nothing. You could pretend that there's another state here that you transition to. You could call it an error state. Do nothing means you don't match, right? So you could represent that in your state machine with a special state called the error state that every other state transition for every other letter in the alphabet goes to. These are usually omitted in diagrams, but you can see this more clearly when we show how to represent this in a table. So what this is saying, we're in state 9, and only if we see a letter do we transition to state 10. Otherwise, we fail to match. You can imagine transitioning to an error state. What about when we're on state 10? What if we see a letter? What state do we transition to? 10. What if we see another letter? What state do we transition to? 10. What if we see a billion letters? What state are we going to transition to? 10. Yeah, so this back edge here kind of looks like that clean closure. That's what represents this cycle in this diagram. And same if we see a digit. So how might you represent this with regular expressions? How might this look, to kind of give a little quiz? how might we represent this? How might a regular expression represent this same pattern matching? Yeah.
Is there like a notation for like a backslash D?
Yeah, let's pretend there is. Let's say it's called letter, and it matches all letters. Or let's just call it L. Let's say L matches all letters, and D matches all digits. How might we write a regular expression that has to see one letter and then sees 0 or more letters or digits after it? Yeah. Okay, so we've got parentheses, letter or digit. The clean closure, star. Yeah, so let's take a look at this. So if we've got I3C, let's say, as our identifier. For the first character, does this match L? Yeah, it matches. And the next character is a 3, so we're inside of this parentheses. Does that match? It does, right? And then we see another C. Does that match? It does. And so, yeah.
So do all of these diagrams have to have them?
So at least in the definition, kind of like definitionally, for automata, there is a final state that's an accepting state. Now that doesn't mean that it can't recognize infinite sequences of things. So for instance, if 10 were the accepting state, then it would accept any length digit, or any length identifier. So at least in the definition of finite state automata, there is an accepting state. Just like with a regular expression, there is a way to know whether you've seen a complete pattern. That's all it really means. But they can be infinite. You can input an infinite sequence of characters. This cycle already makes it possible for an infinite sequence. Yeah.
So if 10 is receiving, why don't we know? Because it's not then.
Yeah, that's a good question. So why not just accept on 10? And this is kind of a technical reason for languages. If I have if I have like x1 equals 3 in my language, or what did I do for simple C? Then we want to know that x1 is the identifier, not x. And so the way this gets encoded, so x will be matched by this, right? Because it's 0 or more L or D. So the way we get around this, the way we ensure that we've seen the longest sequence of letters or digits, is we only accept the match if we've seen any other digit afterwards. Exactly, space. So to make it a little easier to see, so we see x, we see 1, and then only when we see equals in the input do we accept that we've seen the entire identifier. So this is called the look ahead. And if you notice in your toy compiler, there was a variable called look ahead. And so we use the look ahead, we use the next symbol to conclude what a previous set of symbols was in our input. And that's just so that we ensure we match the longest sequence of characters. Yeah?
In our toy compilers, like an example, there weren't spaces in expressions. Is there a way to ignore all white space?
Yeah, so if you look in, I can't remember so Simple C has it, but the way you ignore white space is to just treat it like any other patterns. So if you look at, let me get what was this in the toy compiler? Oh, that's so small. So, it's a little hard to read this, but this is, so you can't ignore the characters because they're real characters, but what we can do is we can match them. So what this lecture does for the second toy compiler, it will match white space tokens. So all of these are special character classes for matching various kinds of white space. So you can actually see that there's actually a space character here. It's a little hard to tell that there's a space character, but there's a space character here. And you can just do the same pattern matching that you do on your other characters. But instead, we just we don't recognize it as a token. We don't produce a token from the lexer when we see that space. So that's how you ignore it. You actually do the matching, you pattern match, but then you just fail to create a token for it, for your parser. And same thing with comments. Comments work the same way. Did I actually put comments? Whoop, that's going to be a solution. Oh wait, sorry, it's in the lexer. What am I thinking? So it's the same way that comments work. So I actually added comments to this language where we can actually match the characters that begin the comment. So comments are treated as white space as well in C and most languages. They're ignored by the token. They're thrown away by the lexer. And so we can actually just literally match the sequence of tokens for the comment. And so, this is divide and multiply, right? These are the symbols for divide and multiply. But if we see them in this sequence, in the input, then we know that we're starting a comment. We're not doing a divide or multiply. So yeah, good question. That's how white space and comments are handled. Yeah?
What files in the compiler were regular expressions?
Oh, the file is is lexer.l. So lexer.l, which I think I still have this open. So this lexer.l, this is all a flex specification is. It's a regular expression. So here's plus or minus or star or divide. It's just regular expression followed by code you want to execute when you see that regular expression. That's all flex gives you. That's all it does. Yeah, good question. Okay, let's do one more complicated one. And let's do one more complicated one. So here is an automaton for matching number symbols in a language. Much more complicated, right? A lot more state transitions, a lot more states. So take a look at it for a second, digest it a little bit. We've got digit symbols, we've got dot, we've got E, we've got different accept states here. We've got plus and minus, other digits. The letter E here, this is literally the letter E. So what kind of number representations might be being expressed here? Yeah?
Scientific notation.
Something like scientific notation. So what's scientific notation? Yeah.
Some number times 10 somehow.
Yeah, so in C, I think it's, what languages? I can't remember what languages have this. But you can actually say E for the exponent in certain languages where you can express, number dot number, do the exponent, and then put another number. And so that's exactly right, something like scientific notation in your language. And so remember, the language definition doesn't say anything about what it actually means. And so if you want to do this language processing or compilers, you need to define what the input language should look like. We kind of take it for granted in C because you just learn it. You learn and it looks like numbers and it looks like math operations. But behind the scenes, there is code that's recognizing that input and defining what input is valid. So we don't have this in our language. We're not going to have scientific notation in our language. But in C, for instance, there are other ways to specify numbers, like 0x. What's 0x in C? What does that mean? Who's seen that? It's hex. It's hex. So you can prefix a number with 0x, and then you can use digits and A and F, A through F, to represent a number. And it's just the lexer matching a different pattern for a different way to represent numbers in your language. Okay, so let's not do the equivalent regular expression. This is way more complicated. Okay, so if this is scientific notation,
Sorry, I was like looking at it and like picking apart. How would you almost like where you see like the period and
Yeah.
How would you almost branch to something else and make it stop there versus like?
That's a good question. Actually, what I was about to kind of ask was, can you represent? So yeah, can you represent just an integer, just like a sequence of digits? With this, will this accept and match just a sequence of digits if I want to represent an integer? Will it match that? And why? Yeah.
Yeah, so when we have some digits and then regressive past state 13,
Yeah.
it won't accept.
But what if I'm on state 18, for instance? Will
You need another symbol of some sort to accept this state.
Right. So could I represent, say, 1, 2, 3 followed by space? Would this accept an integer? Or would I have to put dot and x? Would I have to use scientific notation for the integer, for the numbers in my language?
Not necessarily.
Why?
Because it will accept another state.
So what here shows you that it accepts that? Which state? Yeah. Yeah, 20 and 21. So the kind of subtlety here is that the double circle represents the accept states in the language. And so because we've made accept states that happen before you match the dot and all that, and the E, this can match several patterns of representing numbers in your language. You can match integers, you can match decimal numbers with a decimal point, and because state 21 accepts if you don't, even if you don't have an E, it'll accept that number. And then if you do have an E, you have to have this specific pattern, and then it'll accept that once you see another character. Does that kind of make sense, the design of this? Questions? Yeah.
Are new line characters also?
Say again.
Are new line characters also other characters?
Yeah, new line characters would also be other characters, depending on your language, yeah. What's that?
You do 1, 2, 3 extra and then
That's right, yeah. So in C, all white space is ignored, so you could, you could put things on the same line, put things on different lines, if you have a line continuation. There was someone there with a question.
What do those star characters represent? Are they just the acceptance?
Oh, I think this was just from the text. I took this from the textbook, the Dragon book, so I think those stars, they're probably pointing something out in the text. They're not part of the diagram. Yeah, sorry about that. They're not part of the diagram. That is confusing because it also looks like a clean closure. Yeah.
Is there a way to like in the middle of regular expression to like stop? Like when you branch from 13 to 20, if you're going to use like an or there, how would you make it stop at 20 versus like keep on going to like the next?
Well, I argue there is an or there, right? It's dot, digit, or other. And so whenever you have, we'll get to actually how we model these with graphs, but you can think of two edges out as being an or, one edge out as being an concatenation, and then a cycle somewhere as being clean star. And we'll see how to systematically actually generate these from regular expressions. Okay, so let's take a break here. Let's come back at around 11. Let's say 11. Let's come back at 11 or 11:01. And my machine is starting to freeze up, so I'm going to fix that. And then we'll get into how we can actually translate these into machines. Hi, how's it going?
Hi. So when for the toy compiler 2, when I do make, I don't get any errors. But when I do with the dot backslash exampling, I get a floating point exception.
Oh, on
So where should I check?
Check that example.s. Make sure it matches the expected one we've given you. So we gave you an example.
With that example.s?
Yeah, that shows the complete example. Oh my god. This is not good.
But I just cloned it from online.
All right, so let's get back into it. We left off looking at this more complex example of a finite state machine for recognizing various kinds of numbers in your language. So what we looked at were deterministic state machines, finite state machines. Deterministic state machines are always in one state at any one time, as opposed to non-deterministic state machines, where there can be multiple states at the same time. And that can happen in two ways. Either you have multiple transitions with the same symbol coming out of your state, or you have empty string transitions, epsilon transitions, transitions that always happen whenever you enter that state. So here's a couple examples of non-deterministic finite automaton. Here we see a start state 0, and this epsilon symbol means empty string, so you can always match the empty string. And so as soon as we enter state 0, this machine enters both state 1 and state 3. Non-deterministic, you can't determine what state you're in, any single state you're in. And then, if you see an A or a B in the input, you could potentially be in either 2 or 4. So if you are in state 1 and 3 and you see B, then you're in state 1. Then you're in state 4 because there's no transition from 1 to B. But anyway, this is an example of epsilon transitions to enter multiple states at the same time. And here's an example of having the same symbol used to do two different state transitions. So we're in state 0 here. If we see B, we just continue to go back to state 0. But if we see A, we enter both states 0 and 1. So we can be in multiple states at the same time, kind of like multiple universes or parallel universes or something, however you want to analogize it. But that's the difference between a deterministic state machine and a non-deterministic one. So why would we want to do this? Why would we want to have non-deterministic finite state machines? So let me actually, So let me just define it, and then I'll get to why we would want to do this. Can anyone think of why you would want to do this? What would be the benefit of doing this? Is there a benefit? Yeah.
Can you represent like quantum level things? Because like I think electrons or whatever can be in two different places at the same time.
Maybe, but if there were a finite set of states, you could do that with finite state machines as well. So actually, we'll see that these are equivalent, these two things. We'll actually see that these are equivalent. But yeah, let me show how they're used in this automata theory. So first of all, I want to show another way to represent these state machines. So you can always represent them as a table as well, where each row there's one row per state instead of circles. And then there's one column for each symbol in the alphabet. So we have a finite set of states, we have a finite set of symbols in the alphabet, and we can represent state transitions by looking up the current state you're in and the symbol that's causing the transition. So if I'm in state 0 and I see symbol B, then I go to state 0. And so I think this actually represents this machine here. Questions about that? It's just a different representation. You just record. And this is kind of easier for computation, actually computing, because you can imagine making a table in the machine. You can use arrays to make a table in the machine and actually represent your state machine as a table instead of a diagram, which is not so easy to represent computationally. Okay, so we'll see transition tables. Let me move on to actually show. Yeah, I want to make sure we have enough time to get through this. So, all right. So in our compiler, it's the lecture that we use it's the finite state machines are used to automate the job of the lecture. So let me just get into, let me do this construction. Yeah, let me just go into this. Okay. So the way we're going to do this is we're going to process our regular expression. So think of it just like any math expression. You have symbols and operations. So here our operations are concatenation, alternation, and clean closure. And then we're going to translate each one of these into a state machine. And as we'll see, we use non-deterministic state machines for this because it's just easier to represent these operations in our language. So for instance, alternation, we don't have to try to come up with some finite state machine that will model that alternation. We can just use this epsilon transition as a trick to be in multiple states at once. So let me show what these templates look like, and then we'll get into an example, and you'll hopefully see what I mean. So this is what concatenation looks like. If you've got some state machine already, you have two of them already, concatenation is just lining up their end state and their start state, their accept state and their start state. Kind of makes sense, right? If you have A followed by B, then you just have an A transition to a state and then a B transition to a final state. So concatenation, pretty straightforward. Line up the end state of the first one with the start state of the second one. And this is where alternation is easier, I argue, to implement with non-deterministic finite automata. So all you have to do in order to implement alternation in with a finite state machine is to take your two sub-expressions. So if you've already created a finite state machine for those, then you take your two and then just create a non-deterministic transition to both of them at the same time. And so this is why non-determinism is easier to model, because we don't have to think about all the interaction between those two sub-expressions. We can just say, let's explore both states at the same time. And then if one of them kind of wins, one of them matches, then the other one will just go into a state that isn't an accept state. And similarly for the end, once we're in the accept state of one of them, the epsilon transition will just immediately transition into the accept state for the alternation version of the state machine. Hopefully it makes a little sense diagrammatically. Questions about these kind of templates? Yeah. Say again? Yeah, you can think of this. Yeah, you can think of them as simultaneously running, kind of like parallelism or concurrency. You can think of these as like forking two threads, and then both threads will do matching on the input, and whichever one gets to the accept state will, or maybe both will get to the accept state, which is also possible. And then they'll just both transition, they'll kind of merge, you won't need two threads anymore. But yeah, that's a good analogy, is that they're kind of like threads. And then this one's a little bit more complicated. This is how we do clean closure. So let me walk through this a little bit. So we start with, assuming we have some sub-expression, like let's say we're just matching A and we want to match A star, then this is the complete state machine for that expression. And in the start state for the clean closure, we enter both the beginning of our sub-expression and also the accept state. So why is it that we enter the accept state for clean closure? Immediately, yeah. Right, yeah, because you can accept 0 or more. So this immediate transition to the accept state is saying that if we don't see any elements from this, match any elements, we still have validly matched A star. So we're in a state where we try to match the sub-expression, and we're in a state where we accept the match because we don't actually need it. We can 0 or more. Okay, so now we're in these two states. And so if we see something that matches our sub-expression, we'll go to that sub-expression's final state. And if we're in that sub-expression's final state, we're either accepting the whole expression, because once we've seen 1 or 3 or 5 matches for the sub-expression, we're done. But we simultaneously enter the beginning of the sub-expression. So that's how we can model matching any sequence of the sub-expression. We're just always kind of anticipating that we're in the final state once we've had a match, but we're also in a state where we're trying to match the sub-expression. So it's a little to wrap your head around. It's kind of like multiverses. You're in like multiple worlds at the same time, multiple states at the same time, but it's all finite. So it's something we can actually model. Yeah.
Well, what if you like it like a stick map?
If it-
if you had like each star, you could like, I guess it would.
So if we had like A here, and we were at the beginning and we saw B, what would happen? So we're in the except state for A star, but if we saw B, then there in order to continue matching, there'd have to be a transition with some B after our final state. So this, if we were here and we saw B, it would go to an error state, but we'd still be in this state. And then if we see B and there's a valid, like if it's A star followed by B, and we see B, then this will go to an error state because there's no possible state after this. But this one will go to the I've seen a B state. Does that kind of make sense?
Yeah.
I think there was another question here.
Yeah, does the epsilon represent a differing path? I didn't quite hear you.
Yeah, so epsilon is technically the empty string. And so the idea here is that whenever you see an epsilon transition, you just always take it because you can always match an empty string. But it's how we enter multiple states. One of the ways we enter multiple states at the same time. By whenever we're on a state and there's an epsilon transition, we enter both states simultaneously. Okay, so here's an example for A or B, clean star, followed by A, B, B. So concatenation looks pretty straightforward, right? You have A, its sub-expression for A is just two states with a transition on A. And concatenation just lines up the output state to the input state for each of these. We can see here the general pattern for clean closure. Inside there's some sub-expression, whatever you're putting star on. And then we have this kind of complex epsilon transitions that we just described. And inside the clean closure is A or B. And so here's the pattern, this kind of hexagon pattern for the A or B. Okay, so let's actually go through applying each of our patterns to construct this non-deterministic finite state machine for A or B star, and then A followed by B. All right. So here's our regular expression. Now I won't go into too much of the details of the language processing aspect of this, but it would work just like our compiler where we create a parse tree for these expressions, and then kind of in a bottom-up fashion, we traverse the tree and generate the state machine diagrams from it. So we'll start with the parentheses here. And so we're working on A, and the state machine for just recognizing a single symbol is to just make two states and transition on that symbol. That's how you generate for A. And similarly, we can do that for B. We can make the state transition diagram for B. Okay, so now we've got the two sub-expressions for the alternation operator. So let's take a look at our pattern for alternation. And the idea was to take our two sub-expressions and construct these epsilon transitions to enter both states at the same time, enter both sub-expressions at the same time. Here is our start state for the alternation, and they both have epsilon transitions, so we're trying to match both of these sub-expressions at the same time. And whichever ones match, one or both, then we use this epsilon transition to enter the accept state for the entire alternation. Questions so far? Okay, so let's do the complex one. Let's do so now we've got A or B modeled as a finite state machine. a non-deterministic finite state machine. Let's now do clean closure, the complex one. So clean closure looks like this. Once we have our sub-expression created, we create a new start and end state for the clean closure, and then add these epsilon transitions to do that iteration that we described, that iteration where it matches 0 or more of these sub-expressions. So remember, this is our complete alternation here, and then we're going to wrap a clean closure around this expression. We create a start and end state for the clean closure. There's an epsilon transition to the end state of the clean closure, because that represents 0. So here we're going to both have 0 matches, or we're going to enter the start state of our sub-expression to try to start matching our sub-expression. And if our sub-expression successfully matches, we'll be in the end state of the sub-expression. And so in order to match again or finish matching, we either go to our end state for clean closure, which means we're done. If we've seen one or more of these, then we're done. But we also make an epsilon expression to the beginning of our sub-expression to try to match it again. Questions on this? Questions on this? I know this is a little tough to wrap your head around probably, because there's lots of these states you're in at the same time. Yeah, but questions on this? Yeah.
The only way you're like leaving is if you're going to find something that's not A or B, right?
In this example, yeah, that's right. So if you see something that's not A or B leaving here, then that's right. That's right. In this case. Questions on this? Okay, and then the concatenation for the rest of this is pretty straightforward. So this is our whole expression that we just generated, and then we just concatenate it with a state that recognizes A, with a machine that recognizes A. So we just line up the end state of our clean closure with the start state of our machine that recognizes A, and so on. And we do this for the rest of our concatenation. So here's our except state. Questions on this? Yeah.
So, what is the other notation where you had like 2 nodes inside like a gate? Like the examples you were showing for concatenation, there's like state inside of that kind of function.
Do you mean this?
Yeah.
Oh, so this is just kind of schematic. Like if this state here is A, transitions using A from this state to this state. This is the sub-expression. So you can think of this as like, so for instance, here, that first n is this. Like it looks like this. This is that overlapping pattern that you saw. So this first one is like n something, some non-deterministic machine, and this is the second one you're concatenating with. So it's just showing schematically how it's just saying you line up the start state with the end state. That's all it's showing. Okay, let me actually go through an example of what matching a pattern would look like with this state machine. Okay, so let's try to match, let's say we do A, Okay, so let's do one of the examples we had before. I think we had, let's do BA, BB. So first of all, does this string match our regular expression? It does, right? So it's any 0 or more A's or B's followed by A, B, B. So we have 0 or more A's or B's here followed by A, B, B. So let's look at how let's look at the state transitions here. Let's see, how can I do this? So I'll make a little, let's see if I can move these. Not gonna work. Yeah, let's do it that way. All right, so we start in our starting state, and what states do we transition? So we're looking here. We're like our look ahead character. Our next character is B in our input, and we start here. So what state or states do we enter immediately when we're on this starting state? And maybe I should number these to make this easier to reference. So let's call this 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so we're on the 0 state. What states do we enter? Yeah.
1 and 7.
We enter 1 and 7 because this epsilon transition just matches an empty string. We can always match empty string. And so now we go to state 1 and state 7. So we're in both these states simultaneously. What about now? Are there any other states that we can enter without reading inputs? What's that? So 2 and 4, because there's also epsilon transitions from 1 to 2 and 4. So without reading any input, we can always match empty string. We can also move, we'll also move to 1 and 4. Okay, any other epsilon transitions here? What's that? So 5, so what's the transition between 4 and 5? B, right, but no more epsilon transitions, right? So before we've read any characters in our input, we can already move to these states. Okay, so there's no other states we can move to with epsilon transitions. So let's read the first character in our input. So we read B. What state or states do we transition to when we read B? Say again? 4 to 5. So 4 to 5, we can move from 4 to 5 because we're in state 4, 2, and 7 right now. And there's an edge from 4 to 5 that transitions on B. So we know we can move from 4 to 5. But what about state 2? There's no edge to another state, so we can think of this as going to an error state, as not being used. So, oops. So there's no way to transition from 2 to anywhere else from B that in a valid match to this pattern. And same thing for state 7. There's no transition from A or from state 7 using B to transition to another state. Yeah.
Is traversing through epsilon instantaneous? Is that why the word?
Yeah, you can think of it as instantaneous. You can traverse it without reading any input. All right, so now we're on state 5 only. So, and then we can move our look ahead. We've read B, and now we're looking at A. We haven't read it in yet, but we're looking at A. What states, if any, what state or states, if any, can we transition to from 5? Yeah, we can transition to 6. And since there are epsilon transitions from 6 to other states, we can also transition to those. So we have a state transition, an epsilon transition from 6 to 1 and from 6 to 7. So we can transition to both of those states. And are there any other epsilon transitions that we can transition from 1? 2 and 4, right? 2 and 4. So they're epsilon transitions from 2 and 4. All right, so there's no other epsilon transitions. So we're in these 3 states right now. We're looking at A. And so when we read in A, what state transitions happen when we read in A? Yeah, okay, so we're in state 7, and so we see a transition from 7 to 8. So let's do that transition. Where else do we have transitions on A? We've got 2 to 3. And what about state 4? We're in state 4, we see A. Error transition. So we're no longer in a state that's going to lead to a valid match. And we've read in A. And now we're looking ahead at B. All right, so what about state 3? There's an epsilon transition here, right? There's an epsilon transition. So we can go from 3 to 6. And when we're on state 6, what epsilon transitions do we have? The exact same ones we had before, going to 7 and going to 1 again. And so you can see how this machine repeatedly checks to see if our next input matches this sub-expression in the clean star. That's how it works, right? It's in multiple states. And this state is just saying, hey, I'm anticipating, and actually this state will also have epsilon transitions to 2 and 4. And it's just basically anticipating that we're going to see, kind of optimistically anticipating that we're going to see a match for this sub-expression, while at the same time being in another state that says, well, saying that I've already seen all that, I need to match the rest of my input. See what I mean? So it's kind of optimistically trying all valid possibilities in my pattern, in my state machine, while reading the input. So this is why it's a little confusing to think about non-deterministic finite automata, but it's easier to write a diagram that does it, because you can do this systematic way to do it. Okay, so now we're in all these 4 states right now. All right, and we see B in our input. So what next transitions do we have when we see B in our input? So you can just call them out. 8 to 9. So we've got 8 to 9, so B transitions here. We've got 4 to 5 because B also transitioned here. So at this point in the input, we don't know whether we're seeing A or B star or whether we're seeing the end of our pattern. And so the state machine is capturing both possibilities. And these other states, like from 2, there's no valid way to transition on a B, so that's an error state. And same thing on state 7, there's no valid way to transition from a B. And then again, we do the same thing. We take all of our epsilon transitions and we follow them because they don't require any input. So we go 5 to 6, 6 to 7, 6 to 1, and then 1 to 2 and 3 with our epsilon transitions. And now we can again read RB. Right, so I got to move. I didn't move the pointer. So now we're on B again. Okay, so we're in these 4 states. We see B in our input. What state transitions can we do? So I think hopefully you can all see this by now. We have a transition from 4 to 5. There's no valid transition from 2. There's no valid transition from 7. But we have a transition from 9 to 10. And 10 is our accept state. So once we've seen B and moved to whatever the next character is, we've entered an accept state, so we know that this input matches this regular expression by constructing this finite state machine, which will only enter the accept state if we've seen a string that matches our regular expression. Questions on this? Questions? Yeah.
So since we're at like an end,
Yeah.
will the enclosure recognize that and be like, all right, we're just done?
So this depends on your. This depends on kind of the system you're using this regular expression in. So in like the formal theory world, they'll usually put a special symbol that means end of input. So like think of EOF in the systems world. So there'll be a special symbol which does a sentinel, which designates the end of the string, and then that'll be part of your language, and you can use that to say, for all your accept states, if I'm in the end state, I'm done. In like the programming language, there's actually like a kind of whole combination of these regular expressions that's all being matched at the same time. So you can imagine a giant sort of alternation that's matching all your possibilities, and then there is like an EOF character that the lexer uses to determine when you're at the end of your entire input. Kind of makes sense. Yeah. But yeah, we're just going to deal with like single expression. We're going to hand wave the end symbol, but you can imagine that there's a special symbol for the end here, and then we know to stop. Because I think what you point out is that there's still a state here that we're in, and so how do we like not follow that? You could also imagine that there's more. If there's more to this regular, I mean, strictly speaking, if you enter an accept state, you're done. You've successfully matched your pattern. If there's more input, then these state transitions would continue going on. And so it's just up to you to decide how you want to do that. The formal people will put this end symbol to make that easy. Yeah.
Wait, so I was trying to like, so once one like transitions to the end state,
Yeah.
like stop at all other ones.
Well, it depends on your system that you're in. So you could either say there's a special end symbol and use that to determine. You need to know whether your input's over. Really, the real question is your input over? So if we didn't know whether input is over, we'd have to like continue reading until the end of the input. And so we could just assume that there's a special symbol for the end. We need a way to know whether the input's over, basically. That's really all we need to finish this out. And so if the input's over and we're in an accept state, we've successfully matched. If there's more input, then yeah, that's going to be a problem because we're not really matching this. It depends on what your boundaries are for your string. That's all it really comes down to. Questions on this process? Okay, hopefully that made it a little clear and why we use non-deterministic finite automata. Okay, so I went through a demo. Okay, so it turns out that the NFA is, you could actually imagine potentially writing a program, kind of like a multi-threaded program where you execute this DFA in code. You can turn it into a table, like I showed here. And the program for, once you have this table, the program is pretty straightforward. You just have a variable that says, here's my current state. You have a table, and you just say, all right, for my next iteration, I'm going to look up my current state in the table. I'm going to look up my input in the table. And and then that just tells you what states to go in next. So if you're in an NFA, you need, maybe like an array of states that you're in. And then you just loop through that array and say, do all the table lookups every time you do an iteration. Not too hard to write, right? Just state variable and then look up in the table to get your next state. And read from the input all the way. So there's a little easier to write than like having to do while loops and if statements. You can just have a table lookup to tell you what the next states are. And that's one way to implement an NFA. What Flex and a lot of these regular expression engines do is they instead convert it to a deterministic finite automaton. Instead of trying to manage multiple states, which can be, have sort of unknown computational complexity, it turns out that you can actually always reduce any NFA to a DFA. You can always make any non-deterministic one deterministic. And the key insight here is that even though the non-deterministic state machine can be in multiple states at once, these are all finite state machines, so they all have finite numbers of states. So there's only a finite number of ways that you can be in multiple states in your non-deterministic finite machine. See what I'm saying? So even if you're in a million states at once, you're never going to be an infinite number of states. And as a kind of like little discrete quiz, if I've got 10 states, how many different subsets of states can I be in at the same time? How many, can we count how many ways you can be in multiple states in that non-deterministic machine? So how many subsets of states are there? Did you guys learn this in discrete or math? what's there's like a term for that actually, right? You remember what that's called? Power set. Yeah, very good. Yeah, exactly, the power set. So the power set actually tells you the maximum number of deterministic states you'll be in the NFA. You can't be more than the power set of the NFA states. And so we can actually exploit that fact in order to translate the NFA into a DFA. All we have to do is figure out what those combinations of states that we're going to be in. We know it's finite. There may be a lot, but we know it's finite. And if we can figure that out, then we can turn this into a deterministic one. So this gives us the schema for a compiler for regular expressions. We can take our regular expression, translate it with this very formulaic way into an NFA, and then we can, so this is our, oops, and then we can convert that NFA into the DFA, and then it's just a table. And our matching algorithm is just keep what state we're in, read an input, go to the next state. Read an input, look up in the table, go to the next state. And we have this very simple program that we can write in order to do this kind of complex, intricate matching of arbitrary inputs for arbitrary regular expressions. Okay, so the algorithm for doing this is called the subset construction algorithm. And this is it's going off the screen a little bit, but this is the sketch for doing this. The way we do it is we start at the starting state of the NFA. We do just what we did when we ran it. We go to every possible epsilon transition and collect those states. And then we group those states together because that's one of the combinations of states that we can be in the NFA. So we group that together and we just call that a single state in our DFA. We take that one subset that we found and we just make one deterministic state out of it. And then we build up the table by going through each symbol in the language and following the NFA to see the next set of states that we can be in. We do that for every symbol in the language, and we turn all those subset of states that we found, we map them to a single state in our DFA, and voila, we actually have our DFA. So let me show you what that actually looks like in our. So this is what the end result will be. We're going to basically figure out what all the possible valid combinations of NFA states are, and just call that a single state in our DFA. And by doing that, we can actually convert this non-deterministic finite automaton into a deterministic one. And this table, the algorithm is much easier to write for implementing a DFA. It's just while not in except state. Read your character. So state equals start state. Read the character in. Do your table lookup. So the table lookup takes your current state. I guess new state is this, your current state, and the character. And that's it. And if state is error, exit. Otherwise, you just continue. And so that's at least in pseudocode, that's all the code you need to run your state machine and actually match an input to your regular expression. So as soon as you have that table has all the information that's needed in order to match your input and check whether it's part of the regular expression. So if we can get that regular expression into a table, then this is the algorithm. This is like the Lex Flex algorithm. It's just a giant loop that looks up the next state in the table based on the input. And then if EOF and state equals accept state, then you're done. So this is exit 1 because it's bad. This is exit 0 because it's good. But anyway, I don't want to write the actual code, but it's this is the pseudocode for it. That's all you need to do to match regular expressions with any regular expression, as long as you have that table. And so the whole name of the game here is how do we get that table? With the NFA, our table will look like this. We have multiple possible states to enter. That's kind of annoying to program. I mean, you could do it, but what we're going to do is show you how you can turn this into a deterministic table where there's only one possible next state. And the way we're going to do it is we're going to group together all the valid sets of states in the NFA to find, and then just map those to deterministic states. Okay, questions on the goal here? Questions on the goal here? Yeah.
DFAs always be like represented in a table, or is it like a drawing?
Well, so, I mean, the drawing and the table are equivalent. They're just different representations of it. The diagram is not something, I mean, I guess you could make like a graph. I mean, it's just about how you implement it in the machine. So a table is a very convenient implementation at the machine level. You could certainly represent the DFA as a graph as well, and then like use that, say I'm in this node, and then follow that. You could use like link like a linked list kind of data structure. Tables, like easier. They're equivalent. You can map between the two easily. It's like adjacency list versus, graph. It's like just like in I guess CS1, CS2, you guys did graphs. Did you guys do graphs yet? Maybe not graphs yet. But you can model the same data structure with different implementations. Okay, so let's do the set construction algorithm for this example that we have here. Okay, so let me get rid of these current states. We're not reading the input anymore. Oops. Okay, so the subset construction algorithm looks a lot like running, what we just did to run for a specific input. But our goal is to do it for all possible string inputs to this machine. So what we're going to do is we're going to start at the starting state, 0, and we're going to collect the epsilon closure, all of the states that we can reach with epsilon. So what are those states that we can reach? So we're in 0. What states can we reach? 0, 1, 2, 4, 7. We have the whole closure? Okay. And then we write down the epsilon closure here. So 0, 1, 2, 4, 7. We keep that set. So there's one state in our DFA. Yeah.
Is that a 2 or 3?
Oh, sorry about that. This is my bad writing. So this is 1, and this is supposed to be a comma, and 3. Where are you looking at 2? Oh. Sorry. I thought it was my bad handwriting, but you're right. It's the number 2. So there's one of our subsets that we've discovered that is a valid set of states this will be in. And then we take all the characters in our language, which are only A and B in this language. This is a little crowded. Let me make sure I have enough space here. That's going to be our set of states. And actually, I might as well give space to name these. So let's give this a new name in our DFA. So this is our NFA states, and this is our DFA state. So we'll just call it A. So all I was doing was making a new column for the DFA. So this is the state name in our DFA. Okay, so all we got to do is we got to follow the follow the letters in our alphabet. So if we're in all of these states at the same time, 0, 1, 2, 4, and 7, if we're in all of those states and we see an A, what set of states will we enter if we see A? Three A and error. Okay, so we're in those states. If we see an A, we can enter 3. We can enter 8, right?
Yeah. Error.
And that's it, an error, yeah. So error, we won't include the error state in these. These are the valid states of the state machine. So the states we transition to are 3 and 8. So we make a new set, let's call it B, that we transition to. And we're going to transition to 3 and 8. And so we would be in state 3 and 8. And then we take the epsilon closure, the same thing we did when we were actually running this machine. So what's the epsilon closure of states 3 and 8? So there are no epsilon transitions from 8, but there are from 3. So what are they? What are the epsilon closure? 6. Also 1, good. So we have this back edge, this epsilon back edge. And because we're in 1, we also have 2 and 4 and 7, because we have 6 to 7. So if we're in any of these NFA states and we see an A, then we're going to enter all of these states in our NFA. And so we can collect this grouping of states. So 1, 2, 3, 4, 6, 7, 7 and 8. And I'm getting ahead of myself. So we can collect all those states, and we can give it a new name, B. And instead of having to write the entire set of states in A, we can just use that new name we gave for that subset for B. Questions so far? This process? Sort of makes sense. We're basically just finding all possible subsets of valid states we have when we make all possible transitions in this graph. Okay, so let's do B. So if we are in 0, 1, 2, 4, and 7, if we're in this state here, and we see B, what set of states do we enter? So, right, we enter 5 and nothing else, right? There's no other possible transitions from these states besides 5. So if we're in DFA state A, and actually let me give these better names here. A is confusing. So let's call these Roman numeral 1 and 2. So if we're in DFA state 1 and we see letter B in the input, the only state we transition to is 5. But via the epsilon closures, we also enter state 6, state 7, state 1, state 4, and state 2. Questions on that? That's just the epsilon closure after we've entered state 5. Questions? So now we've seen a new subset of states. 1, 2, 4, 5, 6, and 7. Let's call it Roman numeral state 3. And then we just do this whole process again for Roman numeral state 2. Okay, so if we are in, so let me highlight Roman numeral state 2. So that's 1, 2, 1, 2, 3, 4, 6, 7, 8. So if we're in that state, in that set of states, and we see A, what states do we transition to? If we see A, then we're going to go to 3, right? We'll go to 3. And we go to 8. We go to 3, and we go to 8. So we go to 3 and 8. So we're working on this part of the table. We see 3 and 8. If we're in states 3 and 8 and we do the epsilon closure, what states do we enter? We enter 6, 7, 6 takes us to 1, 2, and 4. These are the epsilon closure of transitioning from 3 and 8. And so it's tricky to tell quickly by eye, but these set of states are the exact set of states that we went in here. It's the same state. So 1, 2, 3, 4, 6, 7, and 8. So what this is telling us is that when we are in this state and we see A, we go back to DFA state 2. We're going to re-enter this same set of states. Questions on this? Questions on this? So if we've already seen that subset of states, we don't need to make a new state. You could, but your deterministic finite state machine would have more states than it needs. So you can reuse the same subset you saw before and use the same DFA state for that. Questions? Questions on this? Yeah.
So what's the point of our GM? It just simplifies it.
The point of the DFA is so that when you implement it, you only need to track one state at a time. You don't need to track multiple states. Yeah. That's the point of it. So if we were running this, we'd have to be in all these. We'd have to have an array that keeps all these states and do that many lookups in our table. It would be a slower thing to run. It'd be slower to run. Okay, let's do one more of these. So we're in state 2, or already in state 2, and we see B. So we're in our current states, highlighted in blue, and we see B. What states do we transition to when we see B from these states? Yeah.
5 and 9, so also 6, 7, 1, 2.
Right. So we take this transition here to 5, and this transition to 9. So we know we're going to be going to 5 and 9. And let me update this to the new set of states. So we enter 5 and 9. And through the epsilon closure, we also enter these states. And so do we have a subset of states that we've already identified that matches this set of states? No, right? So there's nothing that has 9. We have not seen this unique subset of states. So we can make a new NFA subset for this. So 1, 2, 4, 5, 6, 7, and 9. And let's call this Roman numeral 4. And we'll replace this with Roman numeral 4. So effectively what we're doing is we're just capturing every possible state that the NFA will be in, every possible partial match of the input that we're being, and the states are preparing for every possible next input that can come. And it turns out that even though you have a non-determinism here, at least for practical applications, you're going to have many, many fewer DFA states here. Okay. So let's do one more row. And let me see if, yeah, okay. All right, so let's do another row here. I know it's a bit of a slog, but let me illustrate this one more time to make sure we can see. Actually, let me leave these in. All right, so we're in state 4. If we see A, what state transitions happen? 2 to 3 happens, and 7 to 8 happens. And so just like before, we enter 3 and 8. Now we saw this before. We saw 3 and 8, and we saw the epsilon closure of it. That's this state here, which is state 2. And similarly, if we're in this state here, if you go through and do the work of looking at this, you'll see that this will end up getting you back into state 3 as well, DFA state, DFA Roman numeral 3 as well. All right, questions on this process? Would you like me to finish out the table? Or is this, all right, finish out the table? Okay, all right, let's finish out the table. All right, so we're in state 4. So let me circle the states to make it easier to see. So 1, 2, 4, 5, 6, 7, and 9. So we're in these states, and we see A. Whoops. We see A. There's only 2 transitions that we can take, 2 to 3 and 7 to 8. That puts us in states 3 and 8. We saw that several times, right? So that's state 2 again. This is the epsilon closure of states 3 and 8. So this puts us into Roman numeral DFA state 2. But what if we see B? If we see B, and we're in Roman numeral state 4, then here are the 2 transitions that can happen from that NFA state. There's no other transitions that can possibly happen. So that puts us into state 5 and to state 10. And I'm pretty sure we have not seen that before. That puts us into 5 and 10. And so in order to compute all the possible NFA states that we'll be in from 5 and 10, we again do the epsilon closure. So we're in 5 and we're in 10. The epsilon closure gives us 6 and 7, 1, 2, and 4. We haven't seen this subset yet, so we make a new subset for this. 1, 2, 4, 5, 6, 7, and 10. Let's call this Roman numeral state 5. And so if we're in Roman numeral state 4 and we see B, then we enter Roman numeral state 5, which is also an accept state. Okay, and let's finish this out and go to the fill out the last 2 states here. All right, so if we're in Roman numeral 5, which we're already in, which are already highlighted in blue, what states can we transition into when we see an A? So this will go to an error state because there's no possible way, there's no possible next state. And when we see A, we'll see 2 to 3, and we'll see 7 to 8. We've seen that before, right? We've seen like 3 and 8. That was Roman numeral state 2 when you do the epsilon closure. And what about if we see B from these states? What states can we enter if we see B? So 1 doesn't go anywhere with B, 2 doesn't go anywhere with B, 5 doesn't go anywhere with B, 7 doesn't go anywhere with B, 4 goes to 5, and I believe we've seen that before as well, right? We've seen 4 going to 5. And so that put, well, let me compute it out. So the closure of this is here. 1, 2, 4, 5, 6, 7. And that set state is here. 1, 2, 4, 5, 6, 7. So we've seen that subset of states before. And that's Roman numeral 3. Okay, so we've done the whole DFA construction from our NFA, and we come up with this state table. In order to identify the accept states, those are the ones where the NFA subset has an accept state in it. If there's any NFA accept state, then we've matched the input pattern. It doesn't matter that there are other states in the NFA. And so here's our table. And we can actually diagram this out. So we have a table, so we can implement this in code with that little while loop. But we can also diagram this out by just going through all of the states. Let's see what this will look like. So we can go from the table to a diagram. So state 1 goes to 2 or 3, depending on whether the input is A or B. If we're in state 2 will go back to state 2 if we see an A. But it'll go to state 4 if we see a B. State 3 will go to state 2 if it sees an A. And it'll go to state 4 if it sees a B. State 4 will go to 2 if it sees an A. And it'll go to state 5 if it sees a B. State 5 if it sees a, that looks like a 2. It'll go to state 5 if it sees a B. And state 5 will go back to A. State 2 if it sees an A. And back to state 3 if it sees a B. So sorry, a little compressed. Let me make a better arrow here. Anyway, that's the diagram. Yeah?
Why state 3 go to state 4 again?
Did I make a mistake? State 3. Oh, it doesn't go to state 4. Sorry. It goes back to state 3. You're right. Sorry about that. Sorry, so what he was asking is state 3 goes to state 2 if you see A, and it goes back to state 3 if it sees. So, yeah, this is like the A or B. The B, this is the clean star part, but accounting for the fact that you might see A or B in the input. Anyway, the bottom is cut off. At least the recorded video should show the bottom because I'm recording my whole screen. Questions on this construction of the DFA? Yeah.
Is there an accept state?
Oh, yeah. So the accept state, as we pointed out before, is any state that has the NFA accept state. So state 10 was the accept state. And state 5 in our subset constructor has the accept state. So yeah, good catch. So state 5 is the accept state for this DFA. Questions? Yeah.
When we're doing some estimated geophase, do you want the table or the diagram?
You can do either. You can choose to do either. Yeah, whatever's easier. Probably the table is probably easier. I mean, it's yeah. This I just to show you that. Yeah, to show you what the diagrammatically it'll look like. So yeah, we have many fewer states, less to keep track of, so it's faster to match generally. All right, yeah, there's what it looks like in the slides. All right, so the kind of point here is really the high level point is computational models give you a mental model of your computation, and writing this is a lot easier than writing some complex Python program that has like if statements and while loops in it. And so if you can reduce your problem to an already known problem, then you can use already existing solutions to solve them. And so we looked at one specific case of this with regular languages and how you can model it as a state machine and the translations to do it. So I've given you as homework just to go through one of this exercise. Don't spend too much time on it. I don't want you to suffer through this. Do your best effort. Come to office hours if you have any questions. Go to lab today to go over it again to ask questions. But yeah, just go through it. It's a good exercise to go through. All right, take care, everyone. Have a good weekend.